Okay, this is Giancoli Physics, 7th edition, AP edition. We're in chapter 10, fluids, working on problem number 8. Go ahead and dive in. The problem reads, estimate the pressure needed to raise a column of water to the same height as a 46-meter tall pine tree. Pause the video, take a minute to wrap your brain around that, and see if you can come up with a plan. One of the first things you might consider for this problem is there's a pressure differential created by the column of water they're talking about. They don't specify in the question whether they want absolute pressure or if they want the gauge pressure. So you have a little bit of flexibility in how to answer here. However, since they didn't specify, I would assume they want absolute pressure. So if you look at your equations from your equation sheet, assuming you have one, or look in your book, these are the equations we'll be using primarily for the fluids type problems. You'll notice here over on the side, we have a pressure equation here that's depending on a column of water of a particular height. One of them includes this P naught over here, one does not. Because there is atmospheric pressure around this column of water, we assume, then at the base of the column of water, there will be the pressure they're referring to. At the top of the column of water is where the atmospheric pressure would be. So if we're to draw that, one of our problem-solving strategies is to draw a picture before we start. Doesn't have to be anything fancy. If you know my art skills, you know it won't be. We have a column of water here, reaching the height of a tall tree. The pressure they're asking for is down here to generate that column of water. But up here at the top of the column of water, we have atmospheric pressure. The difference between those two is where this rho GH quantity is going to account for the difference. So we're going to use that. And again, I'm going to assume that they want the absolute pressure. So write down our equation. This is a fairly simple plug and chug, no algebra rearrangement required. The P naught in this case is this atmospheric up top. You can look in your book or search it on your favorite search engine. 1.013 times 10 to the 5th pascals. Pascal is a Newton per square meter. We'll probably need some more room here, so we'll slide this over. The density of water, again, you can reference table 10.1 in this particular chapter, or search it with your favorite search engine, or find it in your textbook. But the density of water is 1 times 10 to the 3rd kilograms per cubic meter. G is the acceleration due to gravity. It's the same as it's always been, 9.8 meters per second squared. And then finally, the height of the tree, 46 meters. It gives all our numbers. Dimensionally, if you look at this, the kilogram meter per second squared, that's a Newton. And then this meter and those meters cubed in the denominator will leave you a square meter in the denominator. That's a Newton per square meter, which is the definition of a Pascal. So dimensionally and the specific units, we're all aligned. We can pick up our calculator and calculate a number. Go ahead and do that and see what you get. Okay, after punching those in, the number you should get, back that off, remind you that's meter squared. The number you should get here is 5.521 times 10 to the 5th pascal. Now, since we're dealing with two significant figures up here, I'm going to round this to a more appropriate number. 5.5 times 10 to the 5th pascal. And again, a reminder here, if they had asked for the gauge pressure, we would not have included this atmospheric pressure here. And we would have just had the pressure due to this column. But given the way they worded it, this should be our answer. And we're all done. Ready for the next.